The net benefits picture should look like this. It should be about 10, right? That's where these things join. And this is price minus marginal cost. Right? That's what this thing is. So your benefits are everything below. If you draw it the way you usually draw it, here would be 10 point whatever it is. Yeah. Here's demand. And here's MC, or something like this. And then there's the other side of the diagram, which I won't worry about for the moment. Then it would be the area under demand and above marginal cost. So the area of under demand and above marginal cost over to 10 is the same as the area under price minus marginal cost and over to 10. So that's the reason why I can take the area all the way down. It's already subtracted marginal cost. It's already out of the picture. So the benefits are the entirety of the greenness. He wouldn't ask you to do this, would he? Would he make you calculate like something like that? That's Stan? Would you make him calculate that? Stan's shaking his head. Okay. That would be too many triangles for them to calculate? You have to do that? Okay. Well, if you take it in the fall, I would have laughed and said draw it and don't bring a calculator. But it's Gordon, so you know the answer. Be prepared to calculate that. How would you calculate it? Yeah, I would do it as two trapezoids. Right. I would do it as two trapezoids. I would take 6 plus, as he's marked it, 2. Right. So I take the lengths, 6 plus 1.905. That's what he's done. It's not 2. It's 1.905 divided by 2. So he's found the average height of the trapezoid and multiplied by the base. And he's done it for both trapezoids. And that is the fastest way to do it. Obviously, you could also create two triangles and right. But I suppose the answer is you bring calculators? All right. So like static efficiency, dynamic efficiency guarantees that you get the greatest amount of present value net benefits. So the dynamic efficiency rule, the allocation between the two periods, is the allocation that gives you the highest benefits in the sense of most present value willingness to pay minus present value marginal costs. That's what it does. The second thing you learn from your graph is more is extracted in the first period than in the second, when the two are identical. Right? So that doesn't have to be true. It's true in the example, and it's true in the example because the two periods are identical. And so the second period is getting discounted. And so it's sort of worth less to have something in the second period by the discount rate, and that's what forces things forward. So now you could guess the answer to one of the other questions. The bigger the discount rate, what happens to the amount in the first period? It's going to get bigger or smaller? Well, try infinity. Suppose the discount rate were infinity. How much stuff would you consume in the second period? Anything? Nothing, right? So just go for the extremes. Suppose the discount rate were 0. Would you consume the same in both periods? The discount rate's 0 now, right? So if the discount rate is 0, look at the equation. Then this wouldn't be here, right? That would be 1. So this is exactly the same as this. So wouldn't you expect that to be the same as that? And it would be. So if you want to think about how the discount rate causes things to be allocated between two periods, try the extremes. They'll give you a really good answer. No. It's really about how much do you value things later rather than today. It doesn't have to do with exhaustibility. It just has to do with are they worth more later or now. So now we have a way of thinking about this type of model, which we credit to Harold Hotelli. There are 3 rules in this model, right? One rule is, which I'll describe in a second, is capital market equilibrium. Second rule is feasibility. Feasibility is just the amount of stuff now plus the amount of stuff later equals the total amount of stuff. That one's easy. The third is flow market equilibrium. That's pretty easy. That's however much stuff you allocate to the first period is demanded in that period. So period by period supply equals demand. Thinking of it in terms of assets, you have this pile of coal, and you have an alternative use of your money, a bank account. We'll keep things real simple. Your bank account pays you 5% interest, right? What about your pile of coal? Would you hold your pile of coal if it had the same value per unit next period as it does this period, and your alternative is to make 5% interest in a bank account? No, why do that? So it must be that the pile of coal earns the same as the bank account. Holding the pile of coal must earn you 5% if the bank account earns you 5%. That's assets market equilibrium. In the stock market, if you look in the newspaper, in the stock market, that's a capital gain. You buy a share of Apple. For the longest time, it paid no dividends. It's not a problem. Why would you hold shares of Apple Computer? Because the price of the shares went up. The only reason to hold them is because you believe the price of the shares will go up faster than the interest rate, what you could make if you just gave the money to your favorite bank. In equilibrium, it has to be the same. In reality, of course, it's not the same. Right? There are many, many stocks. It's uncertain which ones will make money and which ones won't. And there's a whole thing called finance that deals with that. We don't deal with it here. In our world, it's really simple. Things are known for sure. So our pile of coal must earn the same rate of return as we earn in a bank account. That's assets market equilibrium. Now let's think of a really simple asset. It turns out redwood trees are a really simple asset for the reason that they are priced before they are cut. So I don't really have to worry about this marginal cost thing. I can really shove it over into some demand curve like is done here. And I'm now interested in how much the trees are worth. If this is the price of lumber, what you make from the trees, and that's the marginal cost of making lumber from trees, cutting them down, taking them to the sawmill, marking them, the whole bloody thing, right? What's left is the price of the trees. That's the thing we're looking at. If you asked about coal, we would not be looking at that side of the equation. The price of coal is almost always going to be the price of coal delivered somewhere. It's makes a big difference what you're looking at. Here, we're looking at literally the price of the trees. Right? And that price has very simple asset properties. You hold trees for a year, you had better get the same rate of return as if you held a bank account for a year. How can that be? The only way for that to be is for the price of the exhaustible resource, not the product, but the exhaustible resource itself. The price has to go up at the rate of interest. That is O'Telling's rule. That's a simple assets market equilibrium rule. Go the right way. So when would you want to buy a resource? If you thought the price next period is going to be more than 1 plus R times P, you would earn more money owning the resource. Again, I mean the resource, not the product from the resource. If you thought it was less, you'd earn more money by putting the money in a bank account. So the only way you get an equilibrium where everyone doesn't either run to buy the resource or no one wants to own it and everyone runs to buy a bank account is the price has to rise at the rate of interest. And that works very well for trees, by the way. Old growth trees do that. And that's the last line. Price goes up at the rate of interest. And there's actually a picture of the prices of old growth trees. And it does pretty much fit an exponential. So second equation, what you started with, X equals what you consume summed over all the periods. Q is the quantity. And the third equation is that the quantity that gets supplied in the period is the amount that gets demanded in the period. And I put in H some demand shift variable, but you don't need that. You can just take that out for your own purposes. And so you can fold all this into one line. So let's start at the top. The top says I can find the price at any time by just knowing how many time periods I am down the road and knowing the price at the beginning. So now I've got price as a function of price in the first period, P0, and time. I've got quantity equals, for each period equals demand as a function of price. Well, I can plug that in and get quantity as a function of the initial price, the interest rate, and the amount of time. Now I can say the total amount there is, X0, equals the sum over however many periods I'm going to have, times sum of the demand in that period, which is a function of the price in that period, which is a function of P0 times 1 plus the interest rate to the power T. So the whole model collapses into one line. And that's the one line. And I'm going to get you through, and there's our one line. If you knew P0, you'd know everything. Right? It's only one thing to find. And I find it, and I'm going to leave out the choke issue because I don't have enough time to do it. So I find it by drawing a 4-quadrant diagram. It's the last thing I'll talk you through, and then I'll leave you to Gordon's tender mercies. So first quadrant has P0, 1 plus R to the T, and it actually has E to the RT, but let's just say it's 1 plus R to the T and not worry about it. Okay? And that's a line that goes up in an exponential rate. And so if you fiddled with P0, that line would move up or down in a parallel fashion. The second quadrant, where it says demand, has a demand curve. I've drawn it backwards. So the origin's in the middle. If I go for the first quadrant, time comes out this way, which it always does. I look at the second quadrant, price goes up, which it always is going to do, but quantity is coming backwards. So quantity is coming up as it comes towards where I'm going in the room. Yeah? The third one is just a reflector. It's just a 45-degree line. It takes the quantity on the horizontal axis and transfers it to the vertical axis, nothing more. And in the last one, I'm going to construct quantity as a function of time. And here's how... What? Come on. Okay, so here we begin to do it. So I start off at time 0. P0 is the price at time 0. The blue line goes around, it hits the demand curve, comes down to the quantity at time 0, right? Comes down and hits the reflecting line, and now draws the quantity at time 0 in this bottom quadrant towards me. And so at time 0, where the bluish line hits the axis, is quantity at 0. Now I can do this again. All right, now I do it again. I pick some time later. So start off at the time axis, go up to P, E to the RT, right? Go left to the demand curve, that gives you the quantity, come down to the reflecting line, and come all the way back over, and the square closes. And I don't know how I point to things. I'll just redraw it because I can't point. Right? So I've got this box, right? This point right here, the one down in the corner there, that's what tells you the quantity as a function of that time. So here's the axis. Here's the time axis. Here's like 0, 1, maybe that's 2. So by reading over to 2 and down, I can find out, and here's the quantity axis. Maybe this is a quantity of 4 for argument's sake. I can find the coordinates of that bottom point. That's telling me at that time what is the quantity that goes with it as a function of P0. And I can do that again, and I've gone all the way to the highest possible price, which gets the name of the choke price. After that, demand's 0. So choke price chokes off demand. It doesn't choke off the electron. And that answers the question, what is a choke price? The price at which the quantity goes to 0. Right? And now I can connect up with a green line all of those corners of the squares I have. And that last line that I constructed gives you quantity as a function of time. If I found the area under it, here it's above it, of course, that area is the total quantity. It's the sum of the quantities over time. If that area is the quantity you started with, you have an equilibrium. If it's not the area you started with, then you could fool around. You could say, hey, well, I actually started with more stuff. So how do I adjust this model to account for starting with more stuff? Well, if you tried a different P0, a lower P0, you'd find the quantity was larger at every time. And when you redid the whole exercise, you'd get a bigger amount, the original green plus the muddy green, right? So as P0 goes down, the quantity that's consumed over all time goes up, and vice versa. So you could just fiddle P0 until you found the right initial quantity, and then you'd have your equilibrium. That's how you get an equilibrium in the diagram. Sort of a target shooting exercise. Pick a P0, any P0, work your diagram, find out how much quantity is consumed. Is it the right quantity? If yes, stop. If no, if it's too little, right, you're going to consume too little, then you better move P0 down and do it again. You're going to consume too much, move P0 up and do it again. And eventually you will find the P0 that exhausts the initial stock. And then you have the equilibrium. You have all the conditions. Price went up at the rate of interest, supply equal demand period by period, and the total amount you demanded was the amount there was. That's what you get. And we do one example here. What happens if you increase the interest rate? So imagine you have this solution and everything's just fine, and then somebody comes in and says, well, actually, you did it all wrong. The world's different than you think. The interest rate is higher than you thought. So in the first quadrant, the line that goes up at the rate of interest is now steeper. If it's steeper, it means for a given P0, if you start with the original P0, prices would be higher over all time. That can't work, can it? So here's just the picture. So you start off, right? Here's my original P0, and let's assume this was the right P0, and when you did your whole diagram, this area was indeed your stock. And then, magically, you had to do it with a different interest rate. If you left P0 the same, with a higher interest rate, P of T would now be everywhere higher. And so demand would be everywhere, quantity demanded would be everywhere what? Price is higher everywhere, quantity demanded is lower, and so this thing would shift inwards, right? Now you wouldn't use up all your stock. So how do you restore equilibrium? You're not using up all your stock. What has to happen to P0? Go up or go down? I'm not using everything up. There's stuff left over. How do I get to use more stuff? P0 should be which? Higher, lower? Lower, yeah? So the new picture has to look like, right? It's got to start lower and go up faster. So if it starts lower, what will quantity be in the first period, lower or higher? Right? P0 has gone down, so what happens to the quantity at time 0 that you actually consume? Price goes down, quantity goes. So as the interest rate goes up, the resource gets used more in the future or more in the present? Which way? Future or present? Interest rate went up, what happened to price? Initial price went down, initial quantity went up, and so the stuff gets used more towards the present. So the higher the interest rate, the more present loaded the plan will be to take the resource out. And that, I believe, is what Gordon set out for us to do. I'm going the wrong way again. But I think we've gotten what we're supposed to get. This is the last thing he wants to point out. And you could find that out. You could find that out by taking the model you had, price minus marginal cost, and ask what happens as you make marginal cost bigger. Right? And that would give you the answer that you would take out less and potentially in a real world situation leave some of it. And I sort of made it.